So apparently, piston knurling is a popular subject, I guess. So I had no idea that this video was going, touch a nerve like it did. It's insane. So as of today, which is 3 days, 4 days, this video has got 40,000 views. I mean, to me, that's insane. I mean, I know it ain't a lot for some, but for me, 40,000 views on a video I just kind of did on a whim, that's crazy. So I felt like, with the amount of comments and the amount of the same comment, and then Uncle Tony's Garage making a video and his words, putting his 2 cents worth in, I felt like we need to clarify some things and unpack some stuff, because it's clear as a bell that the general population do not grasp thermodynamics, fluid dynamics, cylinder honing and honing techniques, or heat dissipation. These fundamental principles have just been thrown by the wayside, and or the people commenting just have no grasp of these concepts. So we need to unpack some stuff. We're going to look at some examples, and we're going to talk about why that the main comment that kept coming up is just has no foundation, and the argument that Uncle Tony gave also has absolutely zero foundation. So hang loose, and then we're going to get into this whole deal. All right, so let's just start with looking at what Tony said, and then we're going to look at some comments, and then from there, we're just going to unpack this thing, and hopefully we can put it to bed. I mean, obviously, like many other subjects, some things, no amount of evidence will change some people's mind, right? It doesn't matter. They believe X, and it doesn't matter if you have 3 dump trucks worth of evidence, they still believe X. So if you are that guy, great. But for everybody else that actually wants to learn something, that's what we're fixing to do. So let's go.
Have you heard about the Smoky Unit knurled piston debate?
Yes.
Okay, let me throw my 2 cents in here, because I think this is something that everybody has missed. And it's, why would knurling make power? Because it has absolutely nothing to do with taking a piston to wall clearance. It has nothing to do with piston stability, nothing like that. It has to do with reducing the surface area of the skirt to the cylinder wall. So, okay, so think of it this way. My hand is the cylinder wall, and the piston skirt is the piston skirt. So now moving this thing through its paces at God only knows how many cycles a second, right? You're talking about some serious speed. You've got big surface area between the cylinder wall and the skirt. Now, if you knurl the skirt, what you're going to do is you're going to put a bunch of indentations on here, and every indentation is going to create a high spot. And that high spot actually comes in contact with the cylinder wall. Well, think of it this way. Take your hand and put it flat on a table like this, right? And now rub your hand, using even pressure, rub your hand back and forth on the table. Put your palm flat. Now take just the tips of your fingers and just your fingernails and do that same thing with the same effort. And you'll see that it's like, if this is So if you were to rate this as 100 effort, this is 4.
All right. So as you can see, I mean, ultimately, this is where the train leaves the tracks, right? So, um, the example, and I think, and again, this goes back to fluid dynamics. That this is where people's missing it, and then also people don't understand how a piston skirt is designed, and that's another problem that because you don't know that you don't know, then you assume that X, Y, and Z, and that's the problem. There's engineering, and then there's YouTube engineering, and and this is how we get in this mess in the first place. All right, so and I'm gonna put some pictures up here on the screen. So, but before we do, I just want to address uh, Tony's scenario. So forget about the knurling. Just forget about the knurling. The example is, you know, take your hand and put it on the table, and then take your fingernails and put them on the table. Right? That's the example. The problem with that is oil and bearing area, load carrying ability. So, and I mean, this ain't hard to comprehend, but if you're not a machinist and been around machines, you just don't really grasp how this works. But if you've seen videos of my cam grinder, right, and we had the whole entire table off, and we rebuilt the whole entire table assembly, and the table has waves, right? So the whole table sits down on the machine, and it has 2 strips. They're like, well, one's a V way, like a lathe, and the other one's a flat way. So you got a V and a flat, and they have oil on the waves, right? And they're not knurled, they're not flaked, they're not scraped, they're ground smooth V and flat ways. Lathes are kind of similar, and like my box wave milling machine is kind of like that. But the point is, and I was actually surprised myself. So I can take it's got a feed handle that feeds the bed left and right. Well, I can disengage that, right? And I needed to move the bed. I had the handles off, and so I couldn't move the bed. So I just took it out of gear and literally pushed a 1,500-pound bed as far as I wanted to push it with one hand, because bearing area, right? People keep talking about friction and knurling and less surface area and free horsepower and blah, blah, blah. The problem is the piston never touches the cylinder wall. That's the problem. The if your piston is touching the cylinder wall, you won't have a piston long. I mean, it's just how it is, right? So the next problem is when we use the example of my flat hand, you know, pretend like this is a flat piece of steel. Well, if you have a machined surface, a nice flat machine surface, and you have a block of steel that's nice flat machined, and you put some 5W30 down on that table, and you set that block down, you can spin that block, move it around, whatever you want to do. It'll just move all over the place because it's riding on a cushion of oil. Now, and because it has a large weight bearing area, right? Because it's a solid, nice block. If you take that same piece of steel and machine it like a knurling plate, where it's just got little points sticking up, and you put it back down on that machine surface with the same amount of oil on the table, it won't move anymore. Well, why not? Because it lost all of its bearing area. It can't carry the load because it's sitting on all these little points instead of a flat surface. That's the problem with that example. And again, if, like machinists understand this because they deal with this kind of stuff all the time. I mean, like, anybody that's a real machinist has had two gauge blocks in their hand. And it's funny, because like this is just elementary stuff to people that do this kind of stuff for a living. But for everybody else, it just when people say stuff and they give an example, it's like, oh, well, that sounds good, right? That makes sense. Well, it only makes sense because you don't understand the fundamental principles behind what's being said, right? So gauge blocks, and it's a well-known thing that gauge blocks are, they're precision ground, they're flat, they're square, they're parallel, perpendicular, all that. So you can take two gauge blocks, and you put them in your finger, between your fingers, and you can just rub them around, and they'll just move all over the place. Well, if you keep squeezing them and you get all the oil out, them suckers will lock together. And they are there. I mean, they'll lock together. And like when we setting up jigs and fixtures and, height stands and indicators or checking mics or QCing a part, we use gauge blocks. And so we'll just rub them until the oil's gone. And then they just lock together and they'll stay there. I mean, you can throw them down on the table and they won't come apart, But again, it's because of the bearing area. It's nice and flat and smooth. So here, I'm going to put up a picture here of what's actually happening in a cylinder. So if you look, so you can see, so the gray area is the cylinder wall, right? The yellow area is oil. And then obviously you can see the piston and rings. So, obviously the crankshaft is slinging oil up in the cylinder wall, and it's the ring's job to control how much gets by, right? And the only way that it can do that, so you've got in performance stuff, right? And we're going to talk about it and I didn't play his whole video, but I'm going to link Uncle Tony's video in the description of this video so you can go watch the whole thing for context. But he talks about Molly rings, and he said that Smokey was probably using Molly rings that needed a very fine finish, right? This is another internet fantasy. All ring. So let's just pause because here we go again. This is more. We just create more problems. When people say a fine finish, define that for me. What does fine finish mean? I mean, it's like saying I've got an aggressive cam. Well, what does aggressive mean? Terms like fine finish are just like the term aggressive. It doesn't mean anything. And the problem is, I don't care if you've got $35 plain iron rings, you got Molly rings, or a Molly coated top ring, or you have stainless GFX top fuel dragster rings. I don't care. The hone profile will be extremely similar, and I'm going to show you what a home profile looks like, what it's doing. I'm going to show you some profilometer readings, and all of that stuff to make it all make sense. But again, the cylinder must be able to hold oil because that is the bearing area, right? Your piston skirt is never touching the cylinder wall. It is riding on a cushion of oil. So till you get that in your mind, the rest of all of these conversations will be an absolute waste of time because everybody else apparently thinks the piston is rubbing on the cylinder wall. I mean, it's insanity. So, and I've got some new and used pistons that we're going to look at that just clarifies. I mean, you can see the wear pattern. It clarifies exactly what I'm talking about. You can't miss it. I need to have one with a burn up skirt. So when a motor overheats, the piston gets excessively large, right? And it takes up the clearance. There's no more clearance, and now the skirt actually rubs the cylinder wall. And that's where you get, you've seen like galded skirts where there's just grooves straight up and down. Well, it did. That's what happens when the skirt hits the cylinder wall. You get that. But if that doesn't happen and the piston is designed properly, then you're going to get some of these examples that I'm fixing to show you. But we're gonna, before we get to the pistons, we're gonna just try to finish this honing cylinders, right? Because that is where everybody's missing it. And probably back in the 60s, that's where they was missing it. They didn't understand how tight or loose they needed to be to really and here's another problem. So everybody in the comments, Uncle Tony, everybody I've seen makes the claim it makes more power. Not one person. I mean, there's 500 comments on the original video. Not one person has shown me a ABA dyno test. Nobody showed me one. So if the whole world is sure that it makes more power, show me the data, because it doesn't exist. Number one, I'm going to tell you why it don't exist. Because it's fantasy land to start with. It's just absolute fantasy land. Number two, it's unmeasurable. The answer is no, but if you could do something to the piston that would reduce friction on the piston, you couldn't measure it on a dyno. You couldn't measure it with ET at the track. It's too small. I mean, you can measure 5 horsepower on the dyno accurately, but much less than that. It's just, can you? Yeah, but is it real? I mean, because you can dyno today and dyno tomorrow, and it's 3 or 4 horsepower difference. Just correction factors. It's just how it is. So these minute changes are just almost unmeasurable, right? So what happens with a lot of this stuff, unfortunately, is it's just cognitive bias, right? You want it to be true, therefore it's true. I've heard it 1,000 times. Oh man, yeah, I got such cam, and it's the best one. Really? Yeah, man, it's the best one for sure. Well, how many cams did you test? Well, none. Well, how do you know it's the best one? Oh, it just is. It's the Dunning-Kruger effect, right? And that's what's happening here. And I think a lot of times, when people hear something, again, if you say it fast, it sounds good, and then everybody gets on board. But so the next time, and again, this goes back with honing, but a bunch of the comments, like a bunch of the comments, it's to hold oil. So you don't need to hold oil in the piston, right? That's the honing job, right? So the cylinder wall is retaining the oil. The piston is along for the ride. One thing the piston is doing that is another problem in this whole scenario that people they just don't know, right? They don't know. The piston is hot, right? that heat has got to move out of that piston. The only way for that to happen is the heat goes out of the piston into the rings, into the skirt, and into the cylinder wall, and then into the cooling system, and then the cycle continues, right? And that's how it works. If you murder the surface area of the skirt, you just killed the piston's ability to move heat out of the piston into the cylinder wall, right? So now what happens? Well, now your piston gets hot. Well, what happens when the piston gets hot? It swells up. Not only does it swell up, now the dome is hot. It can't move the heat out. Now you run into detonation. Now the lid can get critical temperature and melt or deform, and then it can pinch the top ring. I mean, on and on and on, right? Hot pistons are not our friend. We got to get that heat out. And so as time progresses, piston skirts get smaller and smaller and smaller, and now the piston can't get rid of the heat because it has less and less and less surface area. So the OEs realized this was a problem, and they added piston oilers. So that's why all of these new engines have piston oilers, is because the pistons are getting smaller, skinnier, and they got to get the heat out of the piston. So the only way they can do it, because there's not enough surface area in the skirt anymore, so they can do it with piston oilers. And then, that's another reason why you see a lot of this stuff with oil coolers, because now, it's the oil is doing the job that the coolant used to do. So all of that. But let's look at some examples of honing. And I've got a couple of videos here from a while back that explain the home profile, and then we talk about we honing the block, and we checking it with the profilometer, and we show you the readings and why and how and who. And so look, we got just a couple of short clips. I want to show you them, and then we'll come back and we'll just try to wrap this thing up. But I feel like if I'm not thorough, there's just going to be more questions, and people still going to be confused. So I want to try to make it thorough, so we know, we just cover all the bases of all of these scenarios of why piston knurling is stupid. I mean, it's just, I don't know how else to say it. Piston knurling is stupid. I mean, if you got a 35 model tractor and you're just trying to take up some clearance for some, antique, show deal for the weekends at the old tractor show, that's a different story. But for performance engines and daily drivers that need to live, this is not how you do it. So let's look at a couple of clips, and then we'll be back. Is we have to start with the home profile looks like this, right? And then when we come in with the really fine stones, we just knock these peaks off. So then when it's all finished, none of this up here exists anymore. And this is the problem. So all of those peaks, as the ring is breaking in and the cylinder's breaking in, it's pulling all of these peaks off, and then all that uglies up the face of the ring, and then it goes in the oil and all of that. And so once we get all of these peaks off, then all of this fills up with oil, and now the piston and the ring are riding on this bearing area. So you got all this cushion for the rings and the piston to ride on. But it's important to get that peak off. Look at that, boys and girls. So, yeah, we can, it's going to take how many strokes I said that was?
5.
5. So it's probably going to take 6 or 7. So we 13 on the RPK and 57 on the RVK. You know, we probably need to be around 50 on the RVK and about 10 or so on the RPK. So a couple of more strokes and we should be just absolutely perfect. So I'm really liking that. All right, so hopefully those 2 clips helped visualize what's happening, right? And so if you've seen the profilometer, so you got RPK and RVK, and there's other stuff on the screen, but the 2 main things we want to focus on is RPK, RVK. So the P is the peaks, the V is the valley, right? So if you've seen in that one, and we was working on bringing the peaks down, but again, you know, as the peak comes down, the valley is getting a little shorter too because it's flattening the whole top out, which is what you want because the flatter that top gets, the more surface area, bearing area you got for the oil to be. And we were like 57 on the valley and like 13. Usually I end up in the 48-ish, give or take, on the valley and like 8 to 10 on the peaks. And I see homes, and here's the problem with this. Well, it needs to be very fine. And again, that's nonsense. What we need plenty of valley. I mean, it's almost what we used to think 20 years ago that too much valley would smoke and burn oil and be all this problem, right? And back in the day, again, we didn't know any better. So I've checked like old home jobs, that stuff that hadn't ever been put together, that might have been honed, you know, 10 years ago, 15 years ago. People just got stuff sitting around. And I mean, it's crazy because it'll be like, instead of being 10 and 50, it'll be 25 and 25. I mean, one's too high and one's not deep enough. And if the valley depth isn't deep enough, it's going to go away fast, right? So you need, and the peaks, just like in the first little clip, the peaks are a problem because they ugly up the rings, they ugly up the oil, they tear up the rest of the cylinder because you dragging, the ring is tearing them off. And that's no good for nothing, especially if you got like race rings that's got a Napier second. And if you don't know what Napier is, then you can just Google it. But it's a hook ring. So the face is like a fine hook, and it's scooping all the junk off the cylinder walls, right? It gets all the oil off, the excess oil. And so if the hone is not premium, then a Napier ring won't live anytime. It'll just tear that second ring face up. It'll just, you know. And so it's irrelevant whether you have a plain iron ring or a moly coated ring. It's irrelevant. It needs the same hone job because the hone is not ring specific as much as it is application specific. So for a car that needs to go 300,000 miles that's fuel injected, we want that 50 RV and 10-ish RP. That's perfectly fine. For a 2,000 horsepower turbo LS on alcohol, we might need 60 or 70 RV. And then that same 10-ish or so, 12 RP. And well, why? Alcohol is trying to wash all the oil out of the cylinder already. So you automatically need more. So we need more valley depth to try to help overcome the alcohol washing all the oil away. And if you ever been around alcohol motors, they just destroy everything in 5 minutes. I mean, they are horrible on parts. And so, and maybe some really high boost diesel stuff is going to be similar. You're going to want a lot of lot more valley depth than you would in a streetcar kind of deal. But other than that kind of scenario, again, it's application, not ring material so much. And again, a Molly ring is still the exact same. A standard $35 set or a Molly set is the same ring package. The only difference is the top ring has a Molly coating. Other than that, it's the same rings. So, and there may be some slight differences in manufactured sets, but ultimately it's the same iron ring, nothing super fancy. It just is what it is, right? So hopefully that clears that scenario up. Now we're gonna look at a few pistons, and then I hope we're gonna be done with this thing because it's already longer than I wanted it to be. So the first example is this is a 1.4. This is a piston and rod out of a 1.4 turbo GM dual overhead cam deal. Now the motor had run hot, so that's why we see a little bit of wear on one side, on the thrust side most likely. But so you see that little bitty patch right in the center. So that's all it's touching. And it's not touching the cylinder wall. It's just this spot right here, right down the center, is the load bearing. That is the section that the pressure is on, right? So you can see that. I mean, it's about it might be a half inch wide, and it's probably 3/4 of that skirt length. So that's a very small amount of surface area, right? And you can see the other side just right. I mean, you just barely see it right in the center. All right. So could you imagine that? I mean, that's proper geometry. That piston skirt has been designed, refined, and it is doing its freaking job. When it's hot, it's using almost the whole length of the skirt. So that way the piston is not rocking. It's using all of that skirt up, right? But none of this crap over here on either side, because again, it's when this piston is turned, the tool is going in and out like a cam rider. So it's barrel turned. So it falls away. And these areas out here on the edges never touch. They're never in contact, right? There's no pressure on them. So could you imagine as Jim Bob in his garage using a manual 80-year-old piston knurler and thinking in your mind that you're going to do a better job than that? Really? This is you almost can't see it. This is a 604 GM crate engine. You can see right down there at the bottom a little bit, and then right up the center of the skirt a little bit. Same deal as the other one. Now the pad's a little wider, but now this is a lot bigger piston too. I mean, it's a 4-inch, 430 bore or something. And this piston, and I mean, you see what that skirt looks like. This piston has probably, I don't know, 150 races on it. And we talking about 40, 50, 100 lap, 200 lap races. So it looks that good. And it's got no like coating, no special snake oil, knurling, no, none of that, right? And it looks perfectly fine. Now here, it's getting smaller and smaller and smaller. Now here, you see how short that skirt is. Now this is a brand new piston for LT1 we're doing. These are diamond pistons. They come uncoated. This is a calico coating. We had them done at Calico. because we put their thick coating on because somebody else did the machine work and the block was a train wreck. So we needed to add some skirt diameter to be able to get the piston wall clearance where it needed to be. Here we go again, right? So the piston has a known expansion rate. And the manufacturer tells us that this piston, because they know the expansion rate, needs X amount of clearance, right? That clearance will make this allow this skirt to do its job. So, and I've run thousands of these pistons, and they work just perfectly fine with this little bitty short skirt. I mean, you see how little that is, right? It's a baby, but it's stable. I mean, it's a stable piston, and it works perfectly fine. So we got our skirts built up an extra couple of thousandths to be able to get the piston wall where we needed it to be. We rehomed the block with a proper home profile to hold oil and get rid of the peak so we're not tearing up rings. And I have no doubt that it's going to live a really long life as long as they don't push the heads off of it with the turbo. So, I mean, I hope that all of that makes sense because all of that other stuff that people are saying is just noise. It's just noise. That they didn't. There's no real data. It's just noise. These are really real life examples of what's really happening in the engine. There is no guessing, no thinking about it. And then on top of that, who wants to make sharp edges all over the piston skirt? I mean, that's just like 100 stress risers. I mean, we work all day long to get rid of sharp edges on shafts, rods, corners, and then we're going to take the pistons and put 100 sharp edges all over them while we cutting gashes into the skirt. So anyway, all right, I'm done with that nonsense. I just wanted to just clarify it just for my own sanity to make sure that, I mean, if there wasn't so many comments, I wouldn't have addressed it. But 500 comments, I need, and not all 500 of them was, it's to hold more oil, but so many of them were, right? And many people were just absolutely, I mean, they were sure that they were sure. And, and if I didn't believe it, then I just had to be a moron. And that's okay. I can be a moron. I'm good with that. But hopefully all of that explained it. And I'd love to hear your comments. Keep them civil. And like I say, no shade on Tony or nothing. Look, I make response videos to things that I'm interested in, and I have absolutely no issue at all with somebody else making a response video to something and share their thoughts. So there ain't no issue there at all, Tony. I appreciate you, and he tagged me in, and wasn't like he was over hiding. So I appreciate that 100%, and appreciate you watching the channel. And I hope that this makes sense. And I'd love to hear your thoughts. Thank you so much. See you on the next one.